So let's explore the further code development aspect in the OpenFOAM. Okay, so till now whatever we look at is the fluid flow related solver development, but the OpenFOAM not only restricted toward the fluid flow, one can also establish a solver for a solid mechanics calculation as well. Okay, so in the similar line, we will try to explore how to create a solver in the finite volume environment for a structural analysis point of view. Okay, and couple of the solvers is already available inside the OpenFOAM. So first let's explore what is available inside the OpenFOAM. Okay, so let's go to the release version. So and we going to do this development in the extended version of OpenFOAM. So form extended 4.0, we try to establish few we try to pick up one solver from this and try to modify the solver. Okay, so first let's look at what different type of the solver available here. So if you look at to application area solver, okay, and look at the solid mechanics. Okay, inside the solid mechanics, if you see so many different class of the solvers available, like this elastic based solvers available. So if you look at its file, you come to know that it is a arbitrary crack propagation solvers. Okay, crack may propagate along any mesh interface. Okay, so that is one class of the solvers available in the solid mechanics. Elastic solid thermosolid form also available. So if you read its nomenclature, transient steady state segregated finite volume solver for small strain elastic thermal solid bodies. Okay, temperature is solved and then coupled displacement is solved. Okay, so that is available. Then viscoelastic solid form also available. So if you check, you will come to know viscoelastic small strain solver used for finite volume method using incremental approach. Okay, so this all different class of solvers is available. Okay, now out of that let's try to modify one solver. Okay, so we work with the very simplified solver. So here you will see one is different class of solver that already available. Okay, so depreciated solvers. In this you will see ICO FSI form, then this new context stress form, new stress form, then this stressed form is available. So what we do, we try to add up this stressed form, and this stressed form has a linear behavior, and then in that as a constitutive modeling point of view, we try to modify that linear behavior in terms of non-linearity. So here what we're going to do, we try to add some plastic materials. Okay, and we try to incorporate the plastic failure of the material as a non-linear behavior and try to add up the steady state class of the solver, even though this stressed form is if you look at it, is a transient steady state segregate final solver for linear elastic small strain deformation for a solid body. In case of that, we have a small strain deformation plus the plastic deformation as well, but we want to work only for a steady state class of the version of the solver. Okay, so what we do, we try to add up that solver and modify it based on our requirements. So that is the idea. So let's first clean this area and let copy that solver what we needed. So from the solid mechanics derive from here, we'll try to copy this solver. Okay, so copy into our area. So here I am saying, let's say paste it and let's rename it at present. Later on we rename based on our requirement 005. Okay, and in case of this stressed form, I want to give its different name because we want to add this non-linearity in it. So non-linear, let's say non-linear stress form, that is the name. Let's say we try to pick up for our solver. So non-linear stressed form. Okay, so that is the name I want to give. And immediately first let's compile this, and then we try to understand this stressed form, and then we try to modify it. Okay, so let's first create the template. So immediately I first rename the .c file. Okay, non-linear stressed form, and then let's go to the make folder and try to rename here as well. Okay, so here we have a stressed non-linear stressed form. It's supposed to go into the user application bin. Okay, now let's create the environment from here and try to, and please remember we try to use the F40 okay, for the compilation. So wclean dot all, so we first try to compile it, okay, based on our understanding. And then we try to understand what is available in the stressed form, okay, and then we try to modify the solver. That is the idea. So we able to compile the nonlinear stressed form. Now let's look at the equation what is solved at present in the this stressed form. So first is the momentum balance equations, okay. So considering solid body element, any of the element, okay, the momentum balance equation can be stated as something like del square rho u del T2 equal to del dot sigma, okay, where u is the solid displacement vector, okay. So u is the solid displacement vector, rho is the density, and sigma is the stress tensor, okay. And another part here is this sigma stress tensor. We try to correlate in terms of strain displacement relationship, okay. So it is linear elastic material we going to consider. So sigma is equal to 2 mu epsilon tau trace of epsilon into unit vector, unit tensor, okay, and epsilon is 1/2 del u plus del u transpose. So this is linear in nature, that's why it says linear elastic constitutive modeling, okay. And here you is the solid displacement vector, density, stress tensor, unit vector, and this mu and lambda is the material property called as a lamb parameter. Now if we combine all these three, okay, and then if we simplify it, we will try to get this one governed equations, and that governed equation we try to code it inside the solver, and that is what exactly the stress form look like, okay. So combining all these things and only retain in terms of u, okay. So we don't want anything in terms of epsilon or sigma. If we try to modify in terms of, let's say, only the solid displacement vector, okay, then we come across this few terms, okay. And in this particular terms, okay, we have to treat different way so that we can so ultimately if you look at this is what nothing but del dot sigma. So if you look at this, del dot sigma is nothing but del dot mu del u plus of this part, and this part we try to treat implicitly, okay, for the stability point of view, and this part we try to look at in terms of explicit way, and then to balance the coefficient of implicit and explicit part we try to rearrange this term, okay. So here we add 2 mu plus lambda into del u implicit, and rest part we subtract out from here, minus mu plus lambda. So this is for the stability point of view. Couple of the time people try to look at like this way to balance out the coefficient, okay. So that is how you can see inside the solvers, okay. And then we have a traction boundary condition. Later on we understand that part. So first we try to look at the code up to here, okay. So let's go to the code area. So first go to the this non-linears, that is nothing but our stressed form only right at present. So later on we modify this, okay. This is our basic file .c file, okay. And here we will see couple of the things like we have a read mechanical property one file, okay. So if you look at the read mechanical properties, so go to the read mechanical property file. So inside of that file we try to look at the parameters that is needed for the calculation. So we try to read the Young's modulus, then E, rho and nu, okay. So all these things we try to read, all the mechanical important properties, and then based on that we try to scale down the normalize the Young's modulus, okay. And then we try to calculate the lamb's coefficient mu and lambda, and this is for the thermal part, okay. So if we don't want to involve the thermal, we get rid of this part easily, okay. So we going to simplify it whenever needed in our solver, because in our solver we don't want to take into account the thermal behavior as well. But if you look at here they try to also incorporate the temperature with optional thermal diffusion and thermal stresses. So we don't want to take into account these thermal stresses, so we try to simplify by removing the thermal stresses part from this solver and incorporate the plastic deforming part in it. Okay, so that is the idea. Okay. So this is the mechanical property. Try to read the important mechanical properties. Okay, then along with that, if you see mechanical property, then we have a create field. Okay, read thermal property, we are not interested in thermal. Okay, so we get rid of that part, and then we have a create field.h file. So if you look at create field.h file, we try to construct the this displacement field. Okay, u as a displacement field we try to construct, and this is related to thermal. So anyway, we get rid of that part as well. And then along with that, if you see here, couple of few things we have. Then read stress from control, so you try to read the control, non-linear iterations and anything needed. And at the end we have a calculate stress.h file. So calculate stress.h file is nothing but it will give you the output as a important parameter like sigma and epsilon if needed. Okay, so that is what it's going to give you, sigma and the epsilons whatever we needed. Okay, so all component of the sigma. Okay, and the required thermal is also be there, then thermal stresses is incorporated or subtracted. Yes, so all these things is there and along with that we have a few things inside the folder, that is the traction displacement boundary. So later on we try to explore what it has. Okay, so now if you look at the exactly the code. Okay, so if we look at present whatever is available inside the solver, so basically this is our basic solver. Okay, and here grad u is nothing but gradient of u. That gradient of u is more often needed in this, so that is that gradient of u, and this is the double derivative part. Okay, so this is, if we get rid of the temperature part, remove this part. Okay, so this is exactly the solver, exactly the same equation what we have inside of this PPT. Okay, so this is the same equation at present what we have here. So this equation basically coded here. Okay, so we have a double derivative in time, that term minus, or the term, entire term goes that side. So this is FVM. So if you remember, we have this term. Okay, so this term is implicit. Okay, so few part is implicit and few part is the explicit part. Okay, so FVM is nothing but the implicit part. So we have FVM Laplacian of 2 mu plus lambda. Okay, 2 mu plus lambda u and Laplacian of this one. Okay, so that is what we have. Then FVC is the explicit part, that is this part. Okay, so here it is coded very nicely, and this is about the thermal part, so we need not to worry about the thermal part at all. Okay, so this is how entire thing is coded. So if you look at here, we start the time loop. Okay, and first look at for the calculation of this required quantities, and until it's converged we try to simulate it. Okay, and after the convergence we try to calculate the stresses for the post processing part. Okay, so that is how one can see all these things here. Okay, then important aspect here is the traction. So where this solid, okay, so solid problem always have some type of the tractions, that is the force is applying on some of the walls. Okay, so it is called the traction forces. Okay, so traction forces has a sometime two part, one is based on the pressure and another is based on the tractions. Okay, so traction is the fixed traction force. Okay, it's, and the traction force, if we want to look at, it's nothing but very simple way. If you see, the fixed traction T is can be T is sigma dot n. Okay, so on the n is the surface normal on the boundary. Okay, so if you do that on the, and because we are solving in terms of displacement, solid displacement, so this condition also supposed to be turned out to be in the solid displacement. So we say del dot n, we plug everything out of that, we try to find out in terms of the gradient. So simplify it, and if you look at, we'll see T minus of this all the terms. So this is exactly coded as a traction boundary conditions inside the boundary implementation file. So if you look at traction boundary and try to check how it is coded in the C file. Okay, so exactly it is here. This is all we again reading the mechanical properties and again scaling the E with respect to rho. Okay, then if it is plane stress and plane strain, so either if we work with the 2D or 3D, depend on that, we have a plane stress and plane strain. Okay, N is nothing but the surface normal, okay, that is needed. Gradient of U we calculate, and grade, this is exactly this grade. Okay, that is what we are calculating here. Okay, traction minus of, here one additional part you will see is the pressure. Okay, so if pressure and the normal component of pressure we want to take into account. Okay, so that is what available here. If the pressure is not available, then this pressure is equal to goes as a 0 straight away. Okay, and then we have all these entries, exactly the same equation is coded there. So like that way we able to apply the traction equal to sigma dot n, okay, on the any of the wall. So it is called traction displacement boundary condition. So that is exactly coded inside of the solver like that way. Okay, so this is the basic solver what we exactly have. Okay, now let's try to modify it based on our requirements. So what exactly we need, we want to incorporate some type of the non-linearity in it. Okay, so when we say we want to incorporate some type of the non-linearity in it, so what is the non-linearity? We want to take into account, let's say, non-linear plastic behavior, and here we restrict ourselves for the perfect plastic. So if we look at its proper definition of perfect plastic, it's something like that, where there exists a maximum level of stress that the solid body can handle elastically. Once the maximum level is reached, after that the solid will undergo irreversible deformation without increase in stress or the load. Okay, so it start deforming irreversibly without any incremental load. Okay, so that is what it's called, its limit. Okay, so that is the limiting one another property we required to restrict. Up to that it is elastic, and after that it is the plastic behavior. Okay, so that is what, but ultimately if you look at the solver, and if we want to work in only in the steady state environment, so if you go back to our Organon equations, so if it is steady state, this term goes out. That means we have a del dot sigma equal to 0. That's it. Okay, so if del dot sigma equal to 0, that means this del dot equal to 0. Okay, so we can arrange the term like implicit equal to explicit part. Okay, so implicit equal to explicit part, exactly we arrange like this way, and we add one plastic behavior equation here. But till now whatever you look at is in terms of U. Okay, so that is the displacement vector form. Okay, so U is what? U is nothing but the solid displacement. But when we work with this plastic behavior, we want to go in terms of the incremental displacement. Okay, so in case of U, we try to go towards the du. So du is the incremental displacement, nothing difference. Okay, so why we going for that? Because here we have a del epsilon p stand for incremental plastic strain tensor. So this part is in incremental form, so every entire equation we take into account in terms of the incremental form. Okay, so if we try to look at, then we have implicit part and explicit part in the similar line. Basically this part, and plus we added that plasticity part. Okay, so we take this part on the one side and other part on the another side. So implicit part, okay, that is exactly equal to everything. Okay, and this is of that part. Okay, so this is part we subtract out from the our sigma exact part, so that's part become positive on other side. Okay, so this is how one can quickly look at the equations. Now we want to code this equation in terms of the incremental. So when we want to code this equation inside of it, we require certain few more properties to be taken into account inside the solver. So we step by step try to modify it. So what different modification one can see is something like this way. At present, whatever we have a U. U is what? U is, again please remember, U is the nothing but solid displacement vector. In case of solid displacement vector, right now we're going to work with the incremental solid displacement vector, that is du. So we have to look at that. Now few more limiting properties we require. The material property, yield stress parameter to represent limiting stress value. After that the elastic deformation is stopped and irreversible plastic deformation will start. Okay, so that is the one material property we require. Then plastic terms supposed to be added. Okay, and this sigma and everything goes in terms of incremental way. So when it goes in terms of the incremental way, we have to also define certain things inside the our property file as well. Okay, so few things we have to modify it. So let's start creating this solver. Okay, so what we can do, we try to modify the certain things. So let me first clean this area, and whatever needed we step by step incorporate it and then try to modify it. Okay, so that is the basic idea. So let's start with the basic files. So if you look at our solver, so nonlinear this .c file. Okay, so this is our basic file. Okay, and here first we try to modify the description. So it is no more transient. We want the steady state solver, finite volume base plus linear elastic. Okay, plus we want to incorporate plastic behavior, but we are restricting ourselves for a perfect plastic. Okay, so we incorporating this perfect plastic behavior in it. Okay, so that is what we want to incorporate as a perfect plastic here. Okay, and along with that what we have is definitely be there like a small deformation of a solid body, and we don't want this thermal stresses. Okay, so that is we don't require. Okay, so this is the simple description of our solver. Okay, now let's try to modify it wherever needed. Okay, so let's start with this one file, mechanical property file and create field file. Okay, so let's first try to look at the mechanical property files. Okay, so if we look at the mechanical property files, so how whatever needed we try to implement, whatever not needed we try to delete that part. Okay, so that is what we can see. So one important aspect here is in the mechanical property file we have to incorporate one that limiting material property, that is yield stress. Okay, so that is needed. So let's first look at the read mechanical property file, and inside the read mechanical property files. Okay, so now if you look at the equation, govern equations. Okay, so in the previous case we required the row because it is available here, but now we don't have a row anywhere, so row part we not required. Okay, inside these calculations. Okay, row part we don't required. Okay, so that is not required. Whatever we try to delete that part. Okay, so whatever is not required, we don't require row, so try to comment the row. In case of the row, whatever needed, we required additional files, additional property, not the file. So we say that we, in case of the row, we require the new material property, that is yield stress material parameter. Okay, so we can say that it's some material parameter and it is yield stress. So I say ys is the yield stress. Okay, so I'm defining the ys, that is better, yield stress ys, we are defining y small s. Okay, yield stress we going to read. Okay, that is one thing. Then when we are calculating this, no more, because row is no more available. Okay, so we need not to define this scaling parameter e. So then we have a we are get rid of the thermal part, so this part is no more needed. Okay, so that is fine. This part we can take off. Okay, so nu and lambda, so we take into account the ys. Okay, so mechanical property we able to adapt based on our requirement. This is also no more needed, row. Okay, so but we have to take into account the e. Okay, so we try to take into account the e, Young's modulus we have to read straight away. So we say e equal, we try to read the Young's modulus, but we don't require the row. Okay, so that part we modified. Okay, so what we did, we incorporate new material property, okay, that is yield stress, limiting yield stress. We don't require rho, and we don't want to read the scale version of Young's modulus. We are using the appropriate Young's modulus E straight away. Okay, so that is what we change it. Okay, now what else change? We have to look at in the create field as well. So in the create field, definitely this part no more needed. So let me comment out this part because it belongs to the temperature part. Along with that, now we have to look at in terms of incremental du, okay, not the simple u. Okay, so and the u will be constructed out of the incremental part. That is the idea. So reading the incremental displacement, okay, reading the field u, in case of that we say incremental displacement field du. Okay, so we are reading the incremental displacement field. In case of u, now we work with the du, must read, auto write from the mesh. Okay, and from the incremental field we try to define the displacement field. Incremental displacement field, from that we try to define the incremental field. So let's try to define the incremental field. Okay, so let's first define the incremental field. Okay, reading the displacement field. So displacement field we try to adapt straight away based on du. Okay, so we don't have to read that. Okay, so u we try to fix it, okay, like that way. So but we don't want to read it because we have to develop from the u only, and no more we are reading. So it is just du. Okay, so we are we define the this. So we read the incremental displacement and then we calculate the displacement. That is the idea. Now we have to also read the sigma. Okay, so we try to incorporate the sigma as well. So now how to define the sigma? So some places it maybe it is there, ICOFSI create field, maybe they have a sigma, I not remember, couple of the places they define the sigma. Okay, so let first check how to define the sigma. So it must be available in couple of the solvers. So let's go to this area and search. Okay, so in the create field.h file, wherever they are using sigma, we have to use that. Okay, so here we have this sigma elastic form. So let's look at. Okay, so you where is the sigma du? Okay, same way, gradient u, sun gradient, then epsilon. Here is so symmetric volume tensor. Okay, so symmetric volume tensor field is the sigma. Okay, so let's try to add up from here. Okay, and here we say reading the stress field. Okay, so sigma is nothing but the stress field. Okay, and we say it is a sigma. Okay, so we adapting few lines from other place. Okay, so we adapted the sigma from that area. Okay, and we are reading. Okay, so we are reading, so same way the way we are reading here, where here, so we have to adapt the same thing only because we are reading here. Okay, but we just have to change the name, that's it. And here is the name as a sigma. Okay, so we read the sigma. Okay, in the similar line also read the incremental plastic strain field. Okay, so incremental plastic strain field we supposed to read. Okay, so that is as a so strain field. Okay, so any of the strain field, if we want to look at, just check vector symmetric. So strain field is definitely a tensor. Okay, so tensor field based on the tensor, so volume tensor field only. So straight away we try to add up this line for that part. Okay, so strain field is nothing but the volume tensor field only, and just modify it based on our requirement. So reading what we are reading, the incremental plastic strain. Okay, incremental plastic strain we are reading as a, we give name as a incremental, okay, plastic strain. So and so let's define it as a some incremental. Okay, so definitely D is there. Okay, and it is a strain, so DPS. Okay, let's say DPS incremental. For incremental we have D, and plastic and strain STR. Okay, DPSTR we try to define. Okay, so and DPSTR is our candidate, and here we have to plug it as a DPSTR. Okay, so volume tensor field we define, and we must read it. Okay, and when it's supposed to be in terms of some dimension tensor. Okay, so we define as, let's say, mesh and dimension tensor. So we say dimensionless tensor 0, and here we say DPST. So I think this is going to work, no worry. Okay, so with this we are set with the create field file as well. Okay, so create field file is set. So let me close whatever not needed. So create field file is set, and we also set with mechanical properties. Okay, so both files we are ready with this. Okay, now what else? Okay, so let's try to copy a couple of the things here. Okay, so we have a we no more require this thermal stresses. So let's copy switch off the thermal stresses, create stress form control. Okay, so create stress form control, let it be the same way. Okay, then what change we supposed to observe inside of the main solver? So first of all, we don't require the thermal part, so let me first switch off that thermal part. Okay, so this thermal part, wherever is there, first switch off the thermal calculations. This also no more needed. Okay, so thermal part we cancel out. So thermal stresses we completely switched off. Okay, along with that, now what is needed in these equations? So now it is not a U equation, it is a DU equations. Okay, this part no more needed, because this is now steady state solver. Okay, so definitely we require this part. So let's look at finally how exactly it's look like. So we require this equal to this is what this is definitely implicit part. Okay, is equal to explicit part, and explicit part because of the our plastic strain. So let's try to modify that way. So let me take this entry from here. Okay, so this is our implicit part. It is exactly the same what we needed, 2 mu lambda into Laplacian of it. Okay, so we say that 2 mu lambda, okay, u, and here no more u is there, we work with the du. So please remember. Okay, so we says that it is d du, and here also du. Okay, is equal to, we require this part, no more required. Now this happen to be minus div FVC. Okay, now gradient of u also, it is the gradient of du. So we said that gradient of du ddu, so we try to use same terminology. So gradient of ddu mu into lambda plus I star trans of ddu minus mu lambda ddu, comma, now this divergence of this sigma. Okay, so sigma we have to modify it based on our requirement. Okay, so let's see what is we have here. So this sigma we already using as a sigma, so it's better to give a some different name, that's it. Okay, so we are using some other name, it is just the typo name for that. Okay, so we set with this part. Now we also have to incorporate the plastic deformation part, that is this one. Okay, so plus of this quantity, so let's add that part. It is again in terms of the explicit only. This part on the left hand side we have implicit part, on the right hand side we have a explicit part. So let's add as a explicit only. So let me copy the same thing. Okay, so but it is positive plus of this, and here we require the 2 star of mu of we don't have a gradient of t here, but what property we considered, okay, in terms of read create field file. Okay, that one, which one? This one. So this is the epsilon. Okay, so gradient of that incremental strain, plastic strain, that we supposed to use here. So that is what needed here. We what we required here is the incremental plastic strain. Okay, so incremental plastic strain plus lambda I trans of, no more this required, lambda I trans of incremental plastic strain. Okay, this part is no more there. Okay, and this we say depending on the sigma, depending on the plastic behavior. Okay, so that is why P. So just check, it is appropriate 2 mu into incremental this plastic strain tensor, lambda into I into trans of that plastic tensor. Okay, so we are set with this. Okay, and then we have a initial residuals is du now. Okay, fine, then initial residuals converge till blah blah blah, and after that when it's over, okay, after that we say that u equal to u plus du, that's it, and we able to set the calculation of u as well here. Okay, so that is what we able to calculate from this. Okay, so we set with this u as well. Now what other change we supposed to do is in the calculation of stress dot h file. So let's look at that later on if we require want to fix anything. So calculate stress dot h files. Okay, so no more okay, after that we calculating gradient of u based on u, so we have that, then sigma rho star of this. Okay, so here we have a sigma is equal to few more changes we have to take into account. Okay, so sigma we already have the sigma, okay, because sigma is the part of our create field.h file, if you remember. Okay, so in the create field.h file itself we are we have this sigma. Okay, so this sigma we try to calculate, okay, and try to assemble the sigma based on our requirement. Okay, so what we can do in the calculation field, we have a old sigma, okay, and we have a new sigma, okay, for the calculation point of view. Okay, so we said that whatever the sigma is available, okay, in the previous case we said that it is nothing but the some old sigma, okay, and that is exactly equal to the sigma whatever we have. And here we said that sigma, okay, equal to sigma plus of this quantities. Okay, so no more rho come into picture because it is not the scale one. So we have a 2 mu, and we try to use this based on the incremental form. So ddu, okay, gradient of ddu, okay, and vector field here we require ddu, gradient of du, okay, then lambda and ddu, that's it. So we are set with the sigma, okay, because we are working with the incremental part. Okay, so we require the incremental form of the sigma. Okay, no more this stress part is needed depending on the thermal behavior, so let's comment that part. Okay, so sigma we set with this, because if you look at the sigma, okay, from this now the sigma is also behave in the incremental fashion only. That means the sigma is in terms of the incremental only. Okay, so that's why we say 2 mu and epsilon is nothing but this, but it is depend on incremental this solid displacement. So that's why we are using the incremental part only from here. Okay, so that is how we fix the calculation of sigma. Okay, sigma is set. What else we supposed to look at? We supposed to define few more conditions. Okay, sometime it is needed. So if we want to check that plasticity conditions, then few more calculations we have to take into account, but that is not right now our intention. Okay, so but we are set with these conditions, and that either it is belong to the plastic area or till in the elastic zone. If we want to check, then we have to look at few more material property behavior equations, and we have to define that limit. After that it goes in the elastic behavior form. Okay, so that part one can add in this calculation of stress part. Okay, and depending on that they try to calculate the this limit. What limit calculate? Depending on that they try to incorporate this incremental plastic strain tensor. Okay, so incremental plastic strain tensor, we have to define its nature, how exactly it is happening. Okay, for that purpose we have that one elastic limit. Okay, and above that it goes toward the continuous plastic deformations, and below that it goes toward the elastic deformation. So we have to set that limit inside of the calculation part. Okay, here. Okay, so that things we try to code here. Okay, so for defining that limit I already have that code, so we try to adapt that part. Okay, so this is what we have to incorporate here. Okay, so we have that part, plastic checking limit part. Okay, so we define some additional conditions. Okay, so where we try to look at this square root of j2 and the fractions we define. So this is coming from the solid mechanics part. Okay, and then if this is greater than 1, okay, then we try to quantify the sigma per cell, like depending on our understanding. Okay, then we calculate the tensor as a this particular quantities what we are using in our calculations. So we use that in terms of this. So let me modify it. Okay, so d sigma. Okay, d sigma is nothing but sigma present minus of sigma old. Okay, so let's also incorporate this thing here. Okay, so with the help of that we are set for our required incremental plastic strain. Okay, this thing we need not to change. Okay, so this part is clear from this side. Okay. Now let's try to compile it and check either we get any error or not. Okay. Okay. In case of this, we have a different mechanical property, ys. Okay, so that is correct. So ys we are using. Okay, so ys then 30. Fine, so that is exactly what we want. And then something related to temperature is failing, so line number 115 correct, so we don't require this related to temperature. Now let's compile it. Okay, cannot convert double into this thing. Let's see. In the calculation stress, tensor, this is also tensor, ddu, this is fine, volume ddu. Okay, we are using the same incremental displacement only. Okay, so we are getting this error. I think that is correct because we supposed to construct a new variable at all here. Underscore, let's say plastic. Okay, so we constructed this new variable. Okay, that is correct because we cannot override this in this regard. So our solver is ready to go. Now few more changes required in the traction boundary conditions. Okay, so let's try to add up few things in the traction boundary conditions. Whatever is needed, we try to modify it. Okay, so let's go to the traction boundary conditions. So traction BC. Okay, so we have to modify this traction BC. Okay, so traction BC we have to change in terms of the incremental way, so let it be traction BC only. Okay, but whatever is needed, we try to modify a couple of the things. Okay, so inside the coefficient dot h file we have to modify certain things. So let's try to look at what we supposed to modify. So in the this traction displacement BC, few things we required. Okay, so one definitely we have to incorporate is the reading of this elastic plastic strain tensor. Okay, so that part we have to incorporate along with the this. We are reading the gradient. This is nothing but incremental, so ddu and du. Okay, so that is the gradient. In the similar line, we supposed to also look for the this field. Okay, so let's say what we required, we also required the new field. Okay, and the field name is supposed to be exactly the same whatever we are using here. Okay, in the create field we have this name. Okay, so let's try to add up the same name here. Okay, so think calculate stress tensor, whatever we have this in the similar line, it's supposed to be here. Okay, so we have a p. Okay, and we are reading for volume tensor field like this way. Okay, and it goes as a boundary condition. Okay, wherever needed. Okay, so it goes as a boundary condition. Okay, wherever it is needed. So I think it's supposed to read from the create field file only, so we supposed to have a same name, otherwise it will going to fail. Okay, so that is fine. So now in the gradient calculations we also have to incorporate few more lines. So traction pressure dot this thing fine, mu this is fine, divided by 2 mu minus of 8. Okay, here we try to add few more lines like plus of, let's say we required couple of the things from the this equation traction. So this part we have to add and this part we have to add. Okay, so both the things we supposed to add here as same way as a traction displacement. If you see, so here we have to also add this plastic part. Okay, so that is plus of 2 mu and this incremental plastic strain tensor and plus of this lambda trans of that part. Okay, so that part exactly these two terms we have to add it in the traction displacement here. So that is what we're going to do here. So let's say same way what we have in the similar line, we supposed to have this part. Okay, so let's say control V new, let me close this bracket. Okay, so this is belong to this, let me close this also. So n star, now it is not 2 star mu value. Okay, and in case of this we have a this value. Okay, so this we have a this value. So this part is done. Okay, then plus we have a n star this trans part, this one same way. So let me use the same quantity here. So trans in case of grade u, no more we have a grade u. Okay, it is supposed to be everywhere it is grade ddu. Okay, so here also it is grade ddu, here also grade ddu, here also grade ddu. Now here we require this thing. Okay, so grade u and into length value. So similar line what we have here, this thing. Okay, so we incorporate that part here. Okay, divided by we have 2 mu lambda and its value. Okay, so I think thermal we don't require, so let me switch off the thermal part completely. Okay, so no more we are incorporating any temperature related dependency on the stress file. Okay, so we are set here. So let's try to look at. Okay, so thermal property is unused variable, that is correct, because we no more using that. So let me comment that thermal property area. Okay, so we are set with this property, new solver. So now let's try to use this solver for the calculations. So let's go to the test area. So I'm copying this part, okay, and constructing here new folder. So inside of it we try to simulate our new solver, and for that we try to add up the test case from the available tutorial and the solid mechanics, and for here we have this test case available. So let me straight away copy this, okay, and first let's run this test case with the help of the stress form only. So block mesh and the application we have to run, that's it. So let me try to use this area for, let's say, without using our new solver. Okay, we try to use our release version of the solver. Okay, so let's say block mesh, so we construct the mesh, and then stress form is our solver. So let's, and then check for the output what we have. Okay, so if you go at the end, so let's look at the increment, how it's look like. Okay, so that is how it's look like, and with that let's try to look at all the different portion of sigma. Okay, so this is the how the increment is look like. Okay, now let's try to run the solver, the same test case for our new developed solver. Okay, so if you try to run it straight away, let's see what error we are getting. So nonlinear stressed form is our new solver. So first of all, ys is missing. Okay, so we require the new property, okay, here. So let me first delete this part, mechanical property. Okay, so inside the mechanical property we have to modify the our required property. Okay, so let's add the required mechanical property. So we also going to use the ys that we're going to read here. Okay, so let me incorporate that as well as a mechanical property. Okay, so we using the ys, y capital, s small. So in case of this we say ys. Okay, this is also ys, and this value is something like we considering 3 plus of 3. Okay, so I am adapting this value straight away. Along with that, what needed is okay, so here what else we needed in case of u. Now no more there is u, replace the t, rename it as a du file. Okay, and then so let's say du. Okay, let it be whatever it has. Along with that we also have to create the file for sigma. We are constructing the file. So let's open the sigma, but please in the create field the sigma is what is a volume symmetric field, so no more it is like this way. So here it is not this, but it is a volume symmetric field. sigma, okay, and let it be everywhere as a sigma. We have to specify the boundary condition for sigma. So symmetric fine, but all other places wherever we have attraction, we say it is a zero gradient condition. Okay, so that is perfect condition wherever we have attraction. Okay, so inside the create field, so we are reading this. Okay, volume tensor field, we have this no read, okay, because we are creating within the solver. Okay, so I think that's fine. So let's try to run it. Okay, in sigma 0 something is failing, so let's see sigma. Okay, so that is correct. We have to set its unit as well. Okay, so sigma, we have to set its unit, correct. So let's set the unit. It is 1 minus 1 minus 2. Okay, then this component as well, 1 2 3 3 3 6. I think that will work. That is correct. This part we have to fix it in the scheme folder. Here system scheme, this is also required, correct. So slowly be able to fix that. Then Laplacian of du, that is also correct. What else? Then du is undefined in the solver, that is also correct. We have to define the du inside the solver. Du temperature no more needed. Okay, this is no more a stress form, it is a linear stress form. Okay, and this is for du. Fine, let's see, is undefined. Okay, till we have a stress form as an entry somewhere. So right now let it be a stress form, later on we define it different way. Okay, u is undefined. U is undefined. Okay, so till we are using as a u only, that's why. So let's better we try to rectify it from the solver side. Okay, so stress form, we have a coefficient displacement equation, that is stress form. Read control. Okay, so read control and du, so let it be a du, no more it is a stressed form, it's supposed to be non-linear stress form. So let modify it here also. Okay, fine. Along with that, what else? In .h file we supposed to modify Okay, in this somewhere there is a stressed form. What line we have? Let's see, try to modify it here also. Okay, it is just here, not an issue. Cancel, but it is better when we are cleaning the code, better we are consistent. So let's modify there also. Save it and let first compile our solver as well. And then we try to modify FE solution, okay, this way, and try to run it. So couple of the changes we have to made. Finally it's run. Okay, so try to check what exactly it's look like. Okay, so here we have a du sigma. Okay, this, okay, okay, this is about the plastic behavior. Okay, so all these quantities we have. Okay, so this is how one can quickly code the solver and simulate it